Heluani. He was MIT, where he got a PhD, and then he was postdoc principal in Berkeley. And now he's professor in IMPA. And today he's going to tell us something about Mathieu, Moonshine.
Obrigado, Igor, pelo convite. Obrigado, Carlos. Posso fazer isso em portunhol bem ruim ou posso mudar para o inglês. Tanto faz para mim. I think my English is better than my Portuguese, but posso tentar em português também. Up to you.
So we go for English then.
Okay, then I'll go for English then. All right. So what I want to say here is I came to talk to you about a conjecture. There's no results whatsoever. It's a conjecture. It's a very nice conjecture. I'm very excited about it because it seems we have nice tools to try to attack it. And it's a conjecture that mixes many parts, many branches of mathematics and mathematical physics or theoretical physics. So it's something that appeared in the physics literature just 2 years ago, and hopefully towards the end, I'll be able to state the conjecture at least. All right, so if I understand correctly, you guys have a seminar that is more or less 2 hours, and we can make a short break in the middle. All right, so let me just program this to have that break. Let me just start with the first part with something that should be very, very classical, which is something about Mathieu's groups. So at least I want to give you a construction of a finite group. It's a very interesting finite group. So as a baby example, let's start with the following group. Let's start with this group of symmetries of certain objects. So now you'll realize that I'm very, very bad drawing. But anyhow, let's try to see this. That's more or less. That should do it more or less. Let's see. All right, so that'll do it. Here and something about here. All right, hopefully you can see the front of a dodecahedron there. And let me just give you perhaps the back of this thing. So let's do something like, who knows? And this is the back part that you cannot see on this dodecahedron. All right. So now everyone knows in school they teach us that the group of symmetries, G, preserving of rotations of 3 space, preserving this figure, that group is a finite group and is A5. It's the alternating group on 5 elements. This is something they teach us. This is the group of symmetries of the dodecahedron or the group of symmetries of the icosahedron. But then something that goes overlooked oftentimes is what is this 5? So what if A5 is a group of alternating, so permutations of 5 elements, even permutations of 5 elements. So what are the 5 things that are being permuted by a rotation in R3 that preserves this object? And that's a good question actually. What is this 5 thing? The answer to that question, I find it interesting, and it's something that they don't teach kids when they start school. So let's take one more. In order to answer what is this 5 here, we can play a game. Let's color. There's a way of coloring the 20 vertices of this figure. The figure has 20 vertices. Each face is a pentagon, and I'll color this with 5 colors. Right? So each vertex is each color is gonna have 4 vertices. Right? So let me show you the 4 vertices that are going to be red, and you complete the graph. So this is going to be red, and now I want to have this one to be red. Yeah, that should do it. Now I want this guy. Nope, that's gonna be bad. So let's take this just for a second. That's correct. And then I have this to be red. And finally I take this to be red. These are the 4 red vertices. Right? So the game is as follows. So there's 5 colors. These are the 4, each color gets 4 vertices in such a way that each face gets the 5 colors. Right? Each face will have the 5 colors. So that's a rule. So what you gained is 5 different tetrahedron with vertices are these 4 red vertices. So you have another tetrahedron, which is the yellow one, that has the other 4 vertices. And now the 5 things that are getting permuted are those tetrahedron, those 5 things. So those 5 tetrahedrons that, well, I don't want to mess up this drawing, we're going to do more. But if you join these 4 vertices, by the 6 edges, you're going to get a tetrahedron. And for each color, you're going to have one of those. And any rotation of 3 space, preserving the dodecahedron, will permute evenly those 5 tetrahedron. All right. So that's a nice thing. But now that we have this picture, let me just break up this dodecahedron in 4 pieces. So what I'll do is I'll take apart each of these vertices. So let's start with this piece here. And let's see what we can do. So, yeah. Oh. So let's see. So this is going to be even messier than the other one. Here's the game. That's one. Let's do this other one just once. Oops. Oops. Yes. That should do it. Horrible with this. All right, so this is just these 2 pieces. So this vertex here is this vertex here. This vertex here is now this vertex here. And now we get to see this shadow part are the 2 faces, the 2 pentagons that are on the back here. Then now I get to see them because I ripped apart the thing. So this face here in the front is this pentagon here, and well, we see these 3 faces there. And we have another 2 pieces on the other side, for one corresponding to this vertex and then the other one corresponding to this guy. The point is that we divided the 12 faces of the dodecahedron, as 12 faces, we divided them in 4 groups of 3. Each group is a vertex like this, and the 3 faces that are adjacent to that vertex. Right? So now I can produce a new symmetry of this group G. The symmetry is going to be a new symmetry of this figure, the dodecahedron. It's going to go as follows. Just rip apart this dodecahedron and rotate this thing a third of a turn. Rotate this thing a third of a turn. And rotate the same thing for these other 2 pieces. So you rotate a little bit, and then you glue back the dodecahedron. Right? So what we produced is the following. So that's going to be some element. We had this group G, well, now it was A5. So we had A5 that was inside, let me just put in a finite group instead of SO3, S12, by permuting the faces. So any symmetry of the dodecahedron, what it does, it just permutes around the faces. And this guy is inside of SO3. Now I don't care anymore about SO3. But the point is that inside of this S12, we produce another guy, sigma, who's, well, we're producing Z over 3Z. We generate sigma, which is this operation. And that sigma Q is the identity. So we have this group of symmetries of the dodecahedron that is just coming from rotations of SO3. But now we have this extra symmetry, this extra permutation of the faces that I needed to rip apart this guy to construct. And the group inside of S12, the group inside of S12 generated by this A5 and Z divided by 3Z. This is one of Mathieu's group, is called M12. So that's the baby version of this Mathieu's M24 that I wanted to describe. It's a very simple thing. You just start with a finite group A5 that we all know and love, and we realize it as some symmetries of some geometric object, and, well, we added an extra symmetry that is non-geometric in nature. We needed to rip apart this thing, flip these three things, and glue this back. Right? But it's a very simple construction.
So you rotate all of them simultaneously?
All of them simultaneously 3 times, and then you glue this back. So, yeah, so notice, so for example, we can play this game, right? Out of this picture here, let me draw something that is shared by those guys. So this edge, and this edge, right? They are here drawn as this, and this. And that gets glued to this, and this in this picture. But now if I rotate this guy here, this other guy here, then this edge is no longer glued to that guy. Right? This guy goes back there, and this guy goes, well, goes to the other guy there. So certainly that thing is not inside of SO. But this is one of Mathieu's group. This is my M12. I should give you a warning. I'm going to be talking about 3 subjects. Finite groups is going to be the first half, I guess, because it's going to be the fun part. You can see things going on. Then we're going to talk a little bit about complex geometry. I need to say a little bit about K3. And then I need to talk about infinite dimensional algebras, and I'm going to be very sketchy there. Unfortunately for you, the only subject that I do know is infinite dimensional algebras. I know nothing about finite groups, and I know essentially nothing about complex geometry. So if you have questions, they're more than welcome, but most probably I won't be able to answer. Anyhow, I hope this is clear. Let's move on to M24, which is the actual group that we want to study. So to do the same kind of business with M24, the role of the dodecahedron which is a tessellation of a sphere, right? So this is a tessellation of S2. Now it's going to get played, well, this is a tessellation of S2, which is the same thing as CP1. So in order to produce M24, what I will produce is a different complex curve. It's no longer going to be CP1, S2, and a tessellation of S2. So for that, I'll replace that guy by, so I'll replace CP1 by a complex curve that is Klein's quartic. Now I lost, by moving to Brazil, I lost my English, my Spanish, and my Portuguese, of course. So I don't know which to do. This is quartic. Okay, so Klein's quartic is the following curve. It's a complex curve, therefore it's a real surface, a smooth surface. That is the zeros of the following polynomial. Where now these coordinates, x, y, and z, are homogeneous coordinates on CP2. Right? So this is a hypersurface in CP2, therefore it's a curve, it's a dimension 1, therefore it's a surface. Again. It's a surface of genus 3, smooth surface, you can compute it quickly. And the beauty of that surface is that it has a nice group of automorphisms. The group of automorphisms of, I'll just call Klein's quartics X. Automorphisms of X is, let me put a name for this, I'll just call this L27. So this has many names. PSL2 over F 7, or the same thing as PGL3 over F2. It's a finite group of order 168, simple. The order is 168 and it's a simple group. It's a group of 3 by 3 matrices with entries are in the field of 2 elements, so 0 or 1. They're invertible, divided by multiples of the identity. Or it's the same thing as just 2 by 2 matrices with field over the field with 7 elements with determinant 1 divided by multiples of the identity. The fact that these two guys are the same is non-trivial. But well, this is a notation for this group of automorphisms. It's actually easy to compute. This goes back to Klein. So this result has over 100 years. So that's going to play the role as my group A5 that I have here. So this finite group of 2 by 2 matrices is going to play the role of A5 in the baby version. So now we replaced the sphere by this curve, A5, which were automorphisms of that guy, by automorphisms of this curve, which is SL27. And now I want to tell you what the dodecahedron is. Or rather, I'll tell you what the icosahedron is first. So yeah, so the drawing of the dodecahedron is slightly better. This is a bit nastier. So the picture that you see here is a polyhedral embedding of this curve in R3. So instead of drawing it nicer, what I'll tell you is how to build this drawing. Right? So we'll build this guy using 4 pieces like this. So these are 4 prisms that have 2 triangular faces and 3 square faces. Right? So the bases are triangles, the sides are squares. And we'll have 6 pieces like this. So these are just prisms, use of prisms, where we have 2 square faces here. Right? And then we should have 4 rectangular faces there, but I just divided each one into triangles. I want to have a triangulation. So this guy has 2 square faces and 8 triangular faces. Okay, so the way to build this guy here, what we did is the following. You just place these 4 guys at the vertex of a tetrahedron, of a regular tetrahedron. So these 4 guys are supposed to be in that regular tetrahedron. And then to each one of these square faces here, we are going to glue the square face on this guy with this square face here by attaching one of this. So what we're doing in particular, we're removing these faces, right? Because now in this face is no longer going to appear because I attached something to it. And it's not so trivial as just attaching this guy as it is. As I am attaching this square here to this square here, I'm also twisting this picture there. So that's why is that you see here this triangle, the yellow triangle and red triangle. Hopefully I did it in the right order here. You see, it's going twisted like this. You don't see the bottom face of this triangle yellow here at the beginning, but now you see it in front of you here. And the red one is going to the back, and certainly the white one is certainly going to the back as well. Right? So we're twisting this thing as you're gluing this square face here with this square face here, and you do this for the 6 edges of the tetrahedron using these 6 pieces here. So you get a curve that has genus 3, the 6 cycles. You can guess them what they are, right? Just going around these guys, these 6 guys that you have there. So this is a genus 3 curve. Well, it's a smooth quartic in P2. And well, let's try to look now that we have time. Let's try to look a little bit to that tessellation. So this tessellation there, let's try to compute sort of like this numerical set of data that you have 20 vertices, how many faces, how many edges do you have. And actually, this is something nice because I think this is something that Klein also knew. Probably not the embedding in R3, but I think he had the quotient of the hyperbolic free space, the hyperbolic space by particular tessellation. All right, so let's count vertices. So we have, let's see how many vertices we have. We have 6 for each one of these guys. Right? We have 3 on top, 3 on the bottom. There's 6 of those. And none of these vertices is going to count anything, because any of these vertices is already attached to the spaces of these guys. So we have the 6 times 4. So we have 24 vertices. Right. So I'm just removing any vertex on these guys. So let's look at faces. As I said before, any rectangular face just disappeared because I just drew another rectangular face in front of it. So I'm only left with triangles, right? And now what? Every triangle is still visible. So we have the 2 for these guys, times 4, that's 8, plus the 8 times 6. So faces, there's 2 triangular faces on each one of those guys, times 4, plus the 8 triangular faces on each of the prisms, times 6. That's 48 plus 8, that's 56. Hopefully that's correct. Someone check that those numbers. I'm really bad at drawing and I'm worse at multiplying numbers. All right, so edges. We can play this game in 2 ways. We can either use the fact that we know this is a genus 3 surface and compute the other characteristic, or anyways, I want to get a number out of here that is interesting, which is the following. If you look at each vertex, you'll find out that there's 7 edges going out of it. There's the 3 edges that, because each vertex is a vertex in one of these guys. So you have the 3 edges that go out of that vertex inside of this piece here. And then there's 2 edges that go to along this prism for each one of the 2 prism sides. So there's 4 plus 3, which is 7. So on each vertex, we have 7 edges. So each vertex, there's 7 edges adjacent to it. Okay, so that's, let's do this. So this is 24 times 7, but now I'm counting each edge twice because I counted it for the 2 end vertices. So I need to divide this by 2. This is 7 times 12, which is 70, 88, 84, right? Okay, so that's the number of edges. And if we did this correctly, let's just check that this plus this, that's 70, that's 80, minus this is minus 4, which is good because we have a genus 3 surface. Okay. All right, so okay, so now we have the numerology. Let's play the same game that we had before. So the group PSL27 adds asymmetries of that figure there, of this polyhedron. So this is our dodecahedron. Well, no, this is my icosahedron. I'll tell you in a second what is the dodecahedron. But it adds a symmetry of a polyhedron that has, well, 24 faces, 56 vertices, and 84 edges. And now, well, this statement here, each vertex has 7 edges. Now this means each face is an heptagon. Right, so I'm taking just the dual of that polyhedron there. Wherever you see a face, put the vertex in the middle. Whenever you see a vertex, put a face there and just join them in the same incidence graph. So this is now, this was the icosahedron. Now this guy is going to be playing the role of my dodecahedron in the previous picture, but now drawing this is just impossible. So that's already this is a nightmare, that thing is Anyhow, hopefully, so far, we're doing just very, very elementary mathematics. And just by the fact that PSL2, by the way, I should at least tell you how this group, how is it that this group may possibly act on this? I mean, it sounds like out of the hat, but it's not so hard, right? This is a finite group. If you produce a three-dimensional representation of this group in characteristic 0, if you just represent this guy by matrices 3 by 3 over the complex numbers, then you have an action of that guy is what? Is C3 that goes down to an action on CP2, and now you only need to check is that this polynomial here is invariant by this representation, by this action. And this is actually the way that Klein constructed this thing. He constructed these collineations. He constructed these matrices. He checked that this polynomial is invariant by those things. And that's how you find, well, since this is just an embedding of that curve there, it's easy to check that the PSL27 is going to be acting here, preserving this. But in particular, now that I have this tessellation of that figure, of that curve, then I know that PSL27 sits inside of S24, permuting the 24 faces of this polyhedron. So this is the same thing as S12 before, and we had A5 inside. It's going fast. It's going to be much less than 12. All right, so the same game that we played before. We want to extend this group by some very nice simple group. Well, it's not an extension, just I want to generate inside of S12 and 24 a bigger group by two sets. This guy, I'm adding an extra symmetry that is going to be a symmetry of that polyhedron, but it's not going to be geometric. So how do we do this? Well, the same game. Color D. 84 edges with 7 colors. In such a way that, each face gets the 7 colors. No two adjacent colors. So now each color gives us 12 edges. And now what is the game that we play? This very same thing as before. Divide this polyhedron, you just break it apart, taking each one of these edges. Just pick one of the colors, like the red color. You break it apart by picking all the red edges. You have 12 red edges, and for each edge you have two heptagons that are adjacent to that edge. Just flip them apart. So you flip those 12 guys, glue this back together. So this produces an action of Z over 2Z inside of S24. It's a non-geometric symmetry of this object. Well, or rather it's two. So that's the analog of this Z3, Z divided by 3Z that I constructed before. And now the statement is Mathieu's group. Mathieu's M24 is the group, the subgroup of S24 generated by and sorry? Oh, that's correct. Thanks. Thanks. All right, so this is a construction more than a definition of Mathieu's M24. I needed this construction somehow because I wanted to see this polynomial appearing, because we're going to see this in connection with K3 later. But, so let me say a few words about these groups. I mean, the thing is that finite groups, finite simple groups have been classified there's a bunch of families that are infinite families of groups, like PGLN, PSLN. It's a family of those, ANs, and so on and so forth. But there's a bunch of groups, there's 26 of them that are just sporadic. They don't fit in any nice classification scheme. M24 is one of those. Mathieu was trying to look for groups that are 5 transitive or n transitive. So if you have a group acting on a finite set, you may ask, when is this action transitive? So that means that just for any pair of points, there's an element of the group that sends this point to this other point. But now when you ask, when is bitransitive? So that means for any 2 points, there's one element of the group that sends this any 2 points to this other any 2 points. And now the question is, okay, so what are the simple groups acting on a set of order n that are bitransitive? But certainly, AN seems to be, or SN is going to be a group that is bitransitive. So now the question is, well, for k-transitive groups, which are the simple k-transitive groups? And it turns out that M24 is essentially the only one that is 5-transitive. There's M23, there's a bunch of groups that are 5-transitive, but this is how these groups appear. If you grab the subgroup of M24 preserving one of these faces in this picture, that group is called M23. And if you take the stabilizer of one point in that group is called M22. The same thing for the M12 that I constructed. If you just look at all these permutations of the dodecahedron preserving one of the faces, that's M11, and so forth. And say a couple of more words. This group appears also as the group of automorphisms of the Golay code, if you know what codes are. If you look at the extended Golay code, this group appears as a group of automorphisms. So one last comment about this group is the following, since I don't need this picture anymore, I'll just remove this. Is the following statement. So by definition, we have a 24-dimensional representation of this group, because we have this permutation representation of these 24 faces. So, I mean, you know, when you have a permutation representation of a group, then the sum of these 24 faces is going to be an invariant vector. So certainly that guy is not going to be reducible. But if you quotient out by the sum, you get an irreducible representation. So M24 has a 23-dimensional irreducible representation. And it has a trivial representation of dimension 1. Then the next irreducible representation is of dimension 45. And then you have also its complex conjugate representation. The next one, I forget. Take this with a grain of salt. It's not going to be relevant for our picture, but I think it's 131 or it's 165. One of these two numbers. I forget. Or it's 165. We can go with it. But the point is that, I mean, this representation, the character table for this group is known. If you go to the atlas of finite groups, you're going to find this group, and you're going to find all these representations. But now, how do you construct this 45-dimensional representation? The 24-dimensional representation I just told you. It's a nice thing, it's permutation of faces. The 45-dimensional representation, how do you construct it? I don't know. And I look in the literature and I don't understand the literature. It's just horrible combinatorics, or at least I don't understand in any natural way how to construct this representation. Certainly not all the other ones. So the atlas, for example, what they do is they will just produce you 2 generators of the group, and they'll just give you 2 45 by 45 matrices. And finally, to check the relations, this is a representation. That's not, so I have in mind something more along Lie theory. If you want to construct a representation of a group, say a compact Lie group G, then you know it acts in the flat manifold, you can take some bundles or vector bundles or even line bundles of this manifold, look at global sections. You have a representation. So I have something along these lines. How do we construct natural representations of this group? So knowing just 2 matrices that are 45 by 45, I don't count that as understanding a representation. So let's move on for like 10 more minutes to at least give me a definition of what K3 surfaces are. So, complex geometry. And I'll try to prevent myself saying any physics for a while. All right, so this is going to have a completely different flavor as what we're doing now. So definition: a Calabi-Yau manifold, I would say n-fold, is a compact, connected and simply connected Taylor manifold. So you have a complex and a symplectic structure that are compatible in a natural way. I say compact already. Taylor manifold. Taylor 2n manifold. Such that any of the following holds. Well, the first term class of the tangent bundle is 0. More or less the same thing. You have a global. There exists a global holomorphic volume form. So that's a non-vanishing holomorphic n form. 3. The holonomy of this manifold is SUN. Or 4, the Ricci tensor is 0. So pick your favorite. I'm not interested in Calabi-Yau manifolds per se. I'm interested in a particular subset of those. So definition: a K3 surface is a compact, connected, and simply connected Kähler 2 n is equal to 2. So it's a 4 manifold. I want to be a complex surface, so it's a 4 manifold such that any of the following holds. So read everything there, just n equals 2, any of the following holds. Holds. Just everything here. So it's going to be, 1. So I'll just add a couple of things. M is Calabi-Yau. So in particular, any of these holds. 2. There's a couple of coincidences here. The holonomy is SP1. Just so happened that SU2 is SP1. 3. The manifold is hypercadic. So a Calabi-Yau manifold of dimension 2 happens to have 3 or just a sphere worth of complex structures that are compatible. You can find 3 complex structures that sort of like represent the quaternion in the tangent space. And it's just this coincidence that SU2 happens to be SP1, so the holonomy being SP1 means that you have a hypercadic. So examples of these guys. And these are quite rigid things, so a couple of comments about this. So let me give you the only example that I care about for these manifolds. Is the following: is just take the set of zeros of a polynomial, an homogeneous polynomial. Homogeneous polynomial of degree 4 in CP3. It's very similar to what we have there. Which is now one dimension up. So that's going to be now a codimension one complex manifold. So there's a surface, a complex surface. And if you're unlucky enough, then the set of zeros is going to be singular. But if you just move a little bit the coefficients, if this guy happens to be smooth, it's going to be a K3 surface. And that's essentially all the examples we care about. We just give a couple of comments about this. So I want to stop in 10-2. So let me just say a few comments about this. So you can generalize this. So you can generalize this to a section. So zeros of sections of the anticanonical. Zeros of sections of the anticanonical bundle to any final threefold. CP3 is a particular case of final. In particular, this gives a bunch of families of K3 surfaces that you can look for, because final threefolds, there's a subset of those that are historic final threefolds that you can just describe by polytones, the very special polytones in toric geometry. So the general section of the anticanonical bundle of a toric final threefold is going to be a K3 surface, and you have a large family of those already to play with. And why would you care about K3 surfaces? Well, this is a nice property. If you want to test your favorite conjecture for hyperkähler manifolds are really hard to produce. Compact hyperkähler manifolds are not easy to produce. So if you want to test a conjecture, just test it on K3 first. That's one thing. So having Ricci flat matrix also, it's not a trivial thing to have. So if you want to test things on Ricci flat matrix, if you're differential geometry more than an algebraic geometer, then you can just test on K3s as well. K3 surfaces have this property that any two of them, let me just give one more example that is going to be the same as this anyways, but it's going to get me to that polynomial. A 4-to-1 covering of P2 ramified along a quartic is a K3 surface. So let me give you an example of this. It's as follows. You take x y cubed plus y z cubed plus z x cubed plus t to the fourth is equal to 0. And this guy maps to P2 by mapping to x, y, z. Right, so I'm giving you a map to P2. Whenever this guy is not, so forget about t now. Whenever this guy is non-zero, then t to the 4 is equal to minus that guy. There's 4 solutions to that equation, so this map is generically 4-to-1. And whenever this guy is 0, well, that's ramified along this quartic. Right? Okay, so this is an example. And well, this happens to be K3 also because of this. This is the zeros of an homogeneous polynomial of degree 4 in CP3. But this is the example I want to have in mind for a K3 surface. A couple of comments now, and then we'll just take a break. Now I can just remove this line quadratic from here. It's as follows. So these are going to be random comments, I guess. Any two K3s are diffeomorphic. So we're not so much interested in the differential structure of these manifolds. The complex structure is what's playing an interesting role here. Actually, if you look at, I mean, these are 4-dimensional manifolds, right? And they're Kähler manifold. Let's look at the composition of their cohomology. So they're connected. So the be 0, the first varying number is going to be 0. It's going to be 1, I'm sorry. Just the connected. There's one connected component. I'm asking them to be simply connected, then B1 has to be 0. So H10 and H01 should be both 0. I'm asking them to be Calabi-Yau. So there's a global holomorphic 2 form. So H20 and H02 is going to be a 1. It's dimension 1. Now we'll put Poincare duality. We'll produce here this. And on a 4-dimensional manifold, there's only one guy that is now interesting, which is this cohomology group. And this guy has dimension 20. For all of them. They're all diffeomorphic and they have dimension 20. So the moduli space of K3 surfaces is of dimension 20. There's a 20-dimensional, 20-parameter space of complex surfaces that are K3 surfaces. Only 19 of those are algebraic. There's one direction that is not algebraic. I don't care about any of this for today, for today's talk. But this fact already tells you, oh, it's a nice playground to play with mirror symmetry as well. And, I mean, this thing is just the same thing as if I rotate it 90 degrees. So K3 surfaces are also a nice testing ground for mirror symmetry kind of conjectures. All right. What is anything else that I wanted to say about K3 in particular before moving on? No. Okay. So I think it's a good time to make a break. Let's just come back a bit. Right. It's going to be, you look at delta m minus n again. So this is 0 if m is not minus n. Then we're going to put m, and here we're going to put here we need this invariant bilinear form, that's a number, times the central element k. So this is called the affine Kac-Moody algebra, the loop algebra of G. This is a central extension of the loop algebra of G. If I didn't have this term here, that would be just the loop algebra of G. Okay, so I'm no longer in the geometry, so we'll move this one. So I only would care about that kind of things when G is when G says U2. So let me move up a notch these things. And instead of having only the disk, let's look at a super disk. So now you may ask the question of, let's look at derivations of this algebra, this polynomial algebra here. But now, so this was a disk. This is this algebra here is the algebra of functions on the punctured disk. So let's tensor this with polynomials in an odd variable, theta. So theta is odd, and theta squared is equal to 0. Right? So now this is a super algebra, and I can look at derivations of this super algebra, super commutative algebra. So these are vector fields on the super punctured disk. I'm not going to give you the basics. So there's a bunch of things to look at. There's you can look at derivation. There's essentially 4 kinds of derivations. There's the even derivations that are of the form ln d by dz as we had before. There's zn d by dz as we had before. There's the derivations of the form z n theta d by d theta. This is also even. And there's the odd derivation zn d by d theta and zn theta d by dz. These are odd derivations. They change the parts. So I'm not going to give you this, but the thing is that the basis of all of this algebra gives rise to a Lie algebra. Let's call this Lie algebra L. And again, it has a central extension. This central extension is called the n equals 2 superconformal Lie algebra. Don't ask me why the n equals 2 then. Probably could have been 1. There's only one odd coordinate. But so So the upshot is, let me write you one example of a super extension of Virasoro. At least one should be clear how to write down. So,
sorry, what's this capital N?
Yeah, so this is just a name. This refers to the number of supersymmetries. And it's, in a second, yeah, so this would refer to the number of theta's that you have. So it's misleading that I'm writing 2 when there's only 1. But I'll tell you in a second why that is n equals 2 and not n equals 1. The thing with supercurves is that you may have extra structure. So let me write what is n equals 1 first. Certainly, this algebra, whatever it is going to have that algebra that I wrote there that is the Virasoro-Lie algebra. I actually wrote Virasoro. Because these guys are inside. And the central extension is the same. There's a unique central extension of these guys. So let me write you another extension. So these algebras are extensions of Virasoro. Let me write you another super extension of Virasoro. So we're going to have NMs like Virasoro, generating Virasoro. And now I'm going to write GNs, where n's, and again, take this with a grain of salt. Because, I mean, this is easy to Google if the commutation relations that I'm writing are correct, but I wasn't planning on actually saying this. So this n is a half integer. And it's odd. So these are even elements of my Lie algebra, and these are odd elements of my Lie algebra. So when I write the commutator of two odd guys, A bracket B is not minus B bracket A, it's plus B bracket A. So I already told you how Lm with Ln commutes. I am missing these guys and these guys. And if I'm not wrong, this should be probably an m minus n over 2. G n plus n. And here, I'm going to get this wrong. I'm certain I'm getting this wrong, so over here. This whole cycle might be wrong. Take this with a grain of salt. Person over. Yeah, so anyway, I'm not going to get it out of my head now. But I mean, it's just a co-cycle that is, it wants to look like an m cubed minus n. Actually, I think it's m squared plus n. So this is called the Neveu-Schwarz triad, modulo of getting that co-cycle correctly. Or the n equals 1, super conformal Lie. So this is n equals 2, that guy is n equals 1. And this n equals 1 comes as follows. It comes because this is a subalgebra of derivations here. So this sits inside of derivations of C, of Z, tensor, C, of theta. But they are derivations that preserve a particular form that is dz plus theta d. So the thing is, if you look at the action by Lie derivatives on this differential form, you may look at those derivations that preserve these guys. So when you add, they just multiply by a function on the z's and theta. Then you get a sub-Lie algebra of this, and that's called the n equals 1 Lie algebra. So this is the analogous statement as when you want to define what does it mean to be a holomorphic vector field. A holomorphic vector field is a derivation of, well, it's a derivation of the algebra of functions that preserve the differential form dz. So this is somehow trying to impose some holomorphic condition on some form of holomorphic condition on a superdisk. So if you preserve this form, if you add, when you change coordinates, it's just again a multiplication by a function of z. Well, that's a holomorphic vector field, not an arbitrary vector field. So this n equals 2 Lie algebra happens to be the same as, so now the n equals n Lie algebra is defined as, now the n equals n superconformal Lie algebra is this algebra of derivations of this algebra theta n. Now these theta i's are odd anti-commuting variables. They're odd, and you're looking at derivations of those guys that preserve the form. Preserving this. So that's the definition of the n equals n. And it just so happens, it's a coincidence that if you put n equals 2 there, or you put just arbitrary derivations of this guy, these two algebras are the same. But that's coincidence. But that's why the name n equals 2. So this has to do with the fact that to construct a superconformal supercurve of dimension 2, so these two odd coordinates preserving this, is the same thing as giving me a holomorphic curve with two line bundles such that the determinant is just the canonical bundle of the base. That's equivalent to just giving me one curve with one line bundle, and then you choose the other line bundle to be the star dual. But oops. All right. Okay. So why am I saying this? So finally, well, now you have a notion of what. Yeah, this is called the big n equals n. So let's just stay there. I'm going to tell you in a second what is the n equals. So in this language, the n equals 4 superconformal Lie. So that's what we care about. So let me tell you what this beast will be. I'm not going to write in commutation relation or anything, but what are going to be ingredients of this picture? So of this beast here. It's going to have many copies of this Lie algebra. So in particular, there's going to be one Virasoro that has a Virasoro Lie algebra. There's going to be a copy of one of those guys for G being SU2 or G being SL2C. It's the same thing. So there's going to be an affine Kac-Moody Lie algebra for SU2. So for SU2 we have three generators, J1, J2, and J3. And the bracket of this with this is this, the bracket of this with this is this, and the bracket of, what am I missing? I guess this and this, this and this, and this is minus this. So this, oh, I should put numbers, right? Because I gave you the generators of these guys are what? Are a basis for G and then integer numbers. So we put n's here, n's here, n's here. And these are going to form G hat for G being SU2. We have a bunch of these guys. But now I want to have many copies of these J's, these G's here, that are the odd guys. So there's going to be two sets of those guys. G plus, let me call them with different names. I'll call them G plus, G minus, G bar plus, G bar minus. And these guys are going to have odd integers here. So let's put n, 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 n. So here we have m is an integer number and n is a half integer number. And now these guys are just some odd guys that satisfy some computational relation very similar to this. If you take two of those guys, you will get some Virasoro plus some cosine that you don't care about the specific formula. But the point is that these guys, as a representation of this Lie algebra, they are the sum of the standard representation of SU2, which is two-dimensional, with this other two-dimensional vector. So if you look at the bracket of any of these guys, forget about the m's and the n's. With any of these guys here, you will get the standard action on the two-dimensional module, and then you will sum the indices. So that's the action of this with this. The bracket of this with this will give you some Virasoros, and the bracket of this is just what is constructed there. Right. So that's the n equals 4 superconformal Lie algebra. It's built out of these beasts. There are 4 fermions, your Virasoro, and the 3 currents that are these are called currents, that are the SU2 algebra. So theorem. Theorem. This is sort of like a trivial statement in physics. It's not written down in mathematics, but well, yeah, actually, the way I'm going to phrase it is simply written down in mathematics. I'll make some comments towards the end when we're finished. So let V be. Yeah. So let me, now I'm being very sketchy. I'll tell you how I'm lying. Let V be this vector space that we constructed before. It was, remember, it was the sum of all these cohomologies on the manifold X of this LKJ, IKJ, where X is a hyperkähler manifold. Then n equals 4 acts on V. Well, a priori I could just tell you, I give you this, the trivial action. It could act by 0. But it acts on V such that the central element, remember this is central attention, so there's a C, which is your central element, such that C acts by multiplication by a number, which is 6. Oh, well, no, it's 3/2 the dimension of X. So that immediately says that the action cannot be triggered. So this is very well known in physics. This is the statement that the sigma model we target a hyperkähler manifold has n equals 4 supersymmetry, superconformal supersymmetry. The 2n equals 2 twisted sigma model we target a hyperkähler manifold has n equals 4 supersymmetry. For the purpose of this talk, which I want to get to actually state in the conjecture, what you should have in mind is how these things are constructed. Remember what this space V had to do, or what this bundle here was. This bundle here was a bunch of, so we took this, we took the symmetric algebra of the tangent bundle, the symmetric algebra of the cotangent bundle, and then the symmetric algebra of the tangent bundle. And then we took many, many copies of this. These were infinitely many copies of this basic object. But now on this basic object, so the different case here will have to do with the different indices here acting. So the different indices here will move you from one K to the next K. So forget about the indices now, and let's try to look at the finite dimensional objects that we have here. We have this SU2, and we have these 4 fermions. So the action, just to give you an idea on how this action goes, on a hyperkähler manifold we have our 3 complex structures that commute exactly like the quaternions do here in SU2. So J1, J2, and J3 will act on T by just the 3 complex structures. On T star by their adjuncts. And the same here, and you just extend. Well, what are the odd guys? G plus, G minus, this and this. On a Kähler manifold, we have naturally 4 differential operators that are odd, whose commutation relations are nice. So we have del, del bar, and their duals. So these are going to be these 4 differential operators. Del, del bars, and their duals. So when you take the commutator of 2 of these guys, you'll get the Laplacian, and that's going to be our L naught. Right? So these are the 4 differential operators that appear in the Kähler identities. These are just the 3 complex structures. This is the Laplacian. And their indices, the only thing that they're doing is just moving you around from different copies here. So it's not so hard to believe that there's such an action. It's hard to prove it. If you want the actual theorem, it's a little bit complicated. The theorem is, let me postpone that for a second. But at least the idea that this Sacheli algebra should act here is not so complicated. What it is incredible is the results a couple of years ago. And notice that I haven't given any names. So in the physics literature, Eguchi and company have a paper, 2010, where they noticed this following statement. Let's grab some representations. Oh, I should say, Yeah, I'll take it. I'll say in a second. Representations of n equals 4, irreducible representations, are very well known. Now let's take X to be our K3 surface. So that's a hyperkähler surface. So we have this V that acts. We have n equals 4 that acts there. This is very well known. And we know what are the irreducible representations of n equals 4. So it's natural to try to ask, okay, so let's decompose this. Let's look at the sum over all i's ranging from irreps of n equals 4 of, well, just that representation, vi, which is the ith irreducible representation of n equals 4, times how many times it appears. Let's just try to decompose. We have a representation of a Lie algebra. Let's try to decompose it in irreducible. We know the irreducibles. And actually, the way they did it is much, it's very simple too. The characters of this representation is easy to compute. The character of V is this elliptic genus that I said. Right? Characters is always graded representation. Knowing this irreducible representation means that we know what the characters of each of these VI's is. So the way to compute this decomposition here, this numbers VI, is just by decomposing the elliptic genus into the sum of functions which are the characters of each one of these irreducible ones. So it's not such a hard task. But now, what they noticed is you can sort of like order this I into sort of like a grid, not by the natural numbers, and by accepting the first number, d naught, which happens to be 24, but let's just forget about this. For this, some reasons we need to get rid of this. This 24 has to do with the fact that the Hodge diamond, the whole the rank homology of the manifold is of dimension 24. That's 24. But all the other numbers are as follows. So d1, d2, and etc. They are 90, whatever the other number should be. 2 times, I didn't check in the break if it was 131 or 165, but you get the idea. It was always 2 times the irreducible representations of n24. So someone noticed, hey, the first 5 numbers are just twice the irreducible representation of n24. The 6th one is a sum of 2 of these. The 7th one is, well, it's a sum, you could write it in different ways. Then immediately, I think 2 months later, they already had up to the 10,000 coefficients put in a computer, and they knew that they were all expressible as sums of representations of M24, dimensions of irreducible representations of M24. They even put the twisted characters, because, I mean, these are characters, right? So you can just put an element of the group and expect what the twisted characters would be. These are the Thomson-McKay series. And they also checked that, I mean, up to a very, very large number, that M24 appears there. So the question is why? And now you know what the conjecture is. So now I can tell you exactly what the conjecture is. Well, modulo the fact that you don't really know, I didn't tell you precisely how n equals 4 acts, but what I said I think is more than enough to give an idea of what this action is. But the conjecture is that there exists an action of M24 on B commuting with n equals 4 action. So that's why these irreducible representations are these multiplicity spaces that are up here. So let's take a look at what this if this conjecture is true or not. So I want to say a couple of comments. Why am I'm excited about this? I'm excited because not this vector space, but there exists something that I call CDR. That is a vertex operator algebra. Associated to any manifold. There's a sheaf of vertex operator algebra associated to any manifold. This is called Genet-Roussel complex. This is of Malikov, Sheckman, and Weintraub. So you take the cohomology of this sheaf, and you have a vertex operator algebra associated to any manifold. This is a vector space. Is great. Well, this is a vector space that it comes with a natural. In the case of a Calabi-Yau manifold, it's bigraded. And it's conformal bricks. And this gives this V that we have. So this V has an extra structure that is the structure of having a vertex operator algebra structure. I'm not going to describe what this is. But now these conjectures can be enhanced as saying that M24 should act as automorphisms of this vertex operator algebra, commuting with the natural action of n equals 4 as a vertex operator algebra representation. If you know what that is, great. Otherwise, it doesn't matter. But the thing is that we have some tools as attacking this problem, knowing that this V is a vertex operator algebra. Let me just tell you a little bit of this conjecture from the geometric point of view, what kind of things that you can extract. So, only looking at conformal weight 1. So let's try to look at the piece that has conformal weight 1. The piece that has by degrees 1. I think it's by degree 1, and I think I'll put here charge rate. So inside of this piece in V, so you can quickly check that if you look at this bigraded piece, then it's a big vector space, it's a big vector bundle, where n equals 4 produces, so it's all coming from the first irreducible representation of n equals 4, this 24 guy that you don't care about, plus there's a piece that is h1 of x with coefficients in Tx tensor T star x. So this is a piece of V. Remember, V was this, right? It was HIs of this and this. So this I'm putting in K. So this charge is 1, this is charge minus 1, and yeah, this has 1. And this is one piece of conformal weight 1. So inside of this space, so for any K3, you can quickly check. This is the same thing as this is H1 of X with coefficients in the endomorphisms of Tx. This is an H1, so this is the same thing as traceless endomorphisms of Tx. For a K3 surface, the tangent bundle is stable, so the coefficients in the H1 is the same thing as the traceless one. On the other hand, this is the same thing as the tangent space. So this is a natural isomorphic to the tangent space at Tx to the moduli space of deformations of the tangent bundle of X. So the tangent bundle of X is a sheaf on the manifold X. You can deform it in the moduli space of sheaves, and well, that's a manifold. And this is the tangent space at a particular point in this manifold. This is naturally isomorphic. This manifold here, as I told you, this manifold is a 90-dimensional symplectic manifold, holomorphic symplectic manifold. Hyperkähler manifold. Therefore, the tangent space at any point, well, is of dimension 90, but is now naturally isomorphic to C45 plus C45. So the conjecture in particular, just taking the very first non-trivial piece, says that M24 should act by its 45-dimensional representation, which is unique, plus its complex conjugate on this tangent space to this modular space. This is a very, very, very first statement. And I don't expect this group to act on the modular space itself, but that's, if that conjecture is true, then this should be the 45-dimensional, and this solves the original problem I stated, trying to understand naturally what the representation of this group are. Well, this is a very, very natural construction of this representation. Well, no, we don't know if it acts or not, but if it's true, this is very, very nice. It acts on the tangent space to a manifold. All right, so this is where I more or less came here to talk.
Questions? questions? Comments? Sure. First of all, why do you need? So why do you really need an hyperkähler structure on Max? It's not enough to have a Kähler Calabi-Yau manifold to construct V, for example.
To construct
V.
No, to construct V. So this V as a vertex operator algebra exists on any manifold. You just need a smooth manifold. But then you want to have some nice representations of certainly algebra. So the statement is, on any Riemannian manifold, you will have a nice representation of the n equals 1 vertex algebra. On any Calabi-Yau manifold, you will have a nice representation of n equals 2 the algebra. And on any hyperkähler, you will have the n equals 4. But you need hyperkähler to have the n equals 4. And the numerology only was done only for K3. For other higher dimensional hyperkählers, I mean, you to play and see if there's something.
One question?
Is there something for n equals true? It's proven?
M24 will have nothing to do, right? So this M24 is this coincidence that if you decompose in character of n equals 4. But what it's interesting about that question is that people have started to try to decompose this elliptic genus of Calabi-Yaus now in characters of n equals 2. Because the thing is that I'm missing some pieces here. That is, if you now look at the generating series for this number, right, we started decomposing some modular form. Right? It was a weak Jacobi form. And now you look at the generating series for this number, and this turns out to be some mock modular function. So people got very excited by this. There's a work of, I'm blanking out, Miranda Chang, John Duncan, Jack Harvey, just getting excited about the fact that mock modular functions appear in this context. So people have started to decompose, but it's very young, this subject, you know, and I don't know it to say much about it.
Questions? So let's thank the speaker.